Hi, I'm Cheryl Leach. In this problem, we're going to be approximating the definite integral from 0 to 2 of x squared dx using both the trapezoidal rule and then Simpson's rule. And after we do that, we're actually going to evaluate the exact answer and compare the results. Well, before we begin, let's talk a little bit about what the trapezoidal rule is and what Simpson rules is. Well, both are numerical techniques that will help me evaluate a definite integral. There's some similarities, but there are also some differences. So let's first talk about the similarities. In both rules, you're going to want to find the width of subintervals. And we know that you can calculate the width of any subinterval by using delta x. And that's the same regardless of which rule you use. The other thing that's similar is that you're going to want to be able to evaluate the function at the endpoints of these subintervals. So you're going to want to be able to find what that height is. And the same thing if you're using Simpson's rule. Okay? So those are the similarities. Okay, what are the differences? Well, in the trapezoidal rule, you're going to take this interval and the function values at those endpoints, and you're going to take these 2 points and connect them with a straight line. That's going to create a trapezoid. And so you're going to use the area of that trapezoid to help you approximate the area under the curve. For Simpson's rule, you're going to use 2 intervals, and you're going to take these function values at the endpoints of your subintervals, and you're going to connect them with a quadratic function, or in other words, a parabola. So if you connect all of these points together with a parabola, you can see that you can approximate the area under the green curve by using that parabola. Okay, well, let's talk about what that means for this particular problem. I want to find the integral from 0 to 2 of x squared dx. Right? Well, the first thing that both of these rules have in common is the width of the subintervals. So I want to calculate delta x for this problem. So delta x is b minus a divided by n. In this case, I'll be going from 0 to 2, so b is 2, a is 0, and I'm dividing by 4 because I'm going to separate this by 4 subintervals. And so that means that each subinterval has a length of 1/2. The next piece that I'm going to need for both trapezoidal and Simpson's rule is to find the function values at the endpoints. So let's go ahead and figure out what those endpoints are going to be. Okay. Well, x sub 0, which is my leftmost endpoint, is going to be at 0. The next endpoint, x sub 1, is going to happen 1/2 of a unit to the right, because I know the width is 1/2. So x sub 1 is 1/2. X sub 2 then is 1. X sub 3 is 3/2. And x sub 4 is 2. So those are all of the endpoints of my subintervals. Well, I also said for both processes I need to find the height, or the function value at those subinterval points. So I'm going to look at f of 0, which in this case is going to be 0 squared, or 0. F of 1/2, which will be 1/4. F of 1, which is 1. F of 3/4, f of 3/2, which is 9/4, and f of 2, which is 4. So that's the part that I'm going to be using in both the trapezoidal and Simpson's rule. But again, as we can see from the pictures, they're not exactly the same. So let's talk about when they're different. In the formulas, we're going to have a b minus a over some constant times n. That's going to depend on whether we're using the trapezoidal or Simpson's rule. For the trapezoidal rule, we're going to be using b minus a all over 2n. And for Simpson's rule, it will be b minus a all over 3n. So again, the formula is slightly different. Then we're going to have a sum, and the sum is going to involve these function values. But the coefficients that go in front of these function values are going to be different depending on whether you're using the trapezoidal rule or Simpson's rule. For the trapezoidal rule, the coefficient that goes with the first function value is a 1. And the last one will also be a 1. All the ones in between will have coefficients of 2. Simpson's rule is a little more complicated. Again, you start and finish with a 1. But in the middle, you have a pattern, 4, 2, 4, 2, and so on. 4, 2, 4 in this case. Now let's use the trapezoidal rule to approximate our definite integral. So the integral from 0 to 2 of x squared dx is approximately equal to b minus a all over 2n times the quantity, our coefficient of 1 times f of x sub 0, plus the coefficient 2 times f of x sub 1, plus a coefficient of 2 times f of x sub 2, plus a coefficient of 2 times f of x sub 3, plus a coefficient of 1 times f of x sub 4. Okay, now what are all these values? Well, I know that b is going to be 2, and that a is 0, and I know that n is going to be 4. F of x sub 0, f of x sub 0 I calculated to be 0. F of x sub 1 I calculated to be a quarter. So I'm going to have 2 times 1/4. F of x sub 2 I calculated to be a 1. So I'm going to have 2 times 1. F of x sub 3 I calculated to be 9/4. So I'll have 2 times 9/4. And f of x sub 4, that calculation was a 4. At this point, we have a lot of number crunching to do, but the result is that I have 2.75 for my trapezoidal rule. Okay, let's do the same thing for Simpson's rule. The formula is a little different this time, but the integral from 0 to 2 of x squared dx can be approximated by b minus a, this time all over 3n, times the quantity. Now let's look at our coefficients. 1 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3. And finally, a coefficient of 1 times f of x sub 4. Now, let's see what all of these things are. Well, again, the b is 2, and the a is 0. The n is a 4, just like before. F of x sub 0, we calculated to be 0. F of x sub 1, we calculated to be 1/4, but this time it's going to be 4 times 1/4. F of x sub 2, we calculated to be 1, and so I'll have 2 times 1. F of x sub 3, that was 9/4. And I need to multiply that by 4. And finally, f of x sub 4 was 4. Again, if I do some number crunching on this, it turns out that I get approximately 2.6667. And you know what? This is actually 2 point with a repeated 6 decimal. All right, I can see that my answers are slightly different. Using the trapezoidal rule, I got 2.75 and 2.6 where the 6 repeats for Simpson's rule. Well, this problem is actually a little bit unusual in that I can evaluate this exactly. So let's go ahead and find the exact value. So let's go ahead and try this. I've got the integral from 0 to 2 of x squared dx. This is going to be x cubed all over 3, evaluated from 0 to 2. Plugging in my upper limit, I'm going to have 8/3, and plugging in my lower limit, I have 0, for a total of 8/3. Now, how does this compare to my other answers? Well, even though I have this written in decimal form, and I did this because Simpson's rule is a numerical process, but 8/3 in decimal form is 2 with a repeated 6. So these two values are exactly the same. Simpson's rule was a really good approximation. The trapezoidal rule didn't do too badly either, but you can see it's a little bit off. In this particular problem, notice in Simpson's rule we approximate using parabolas. In this problem, the function was a parabola. That's why Simpson's rule works so well. I hope this was helpful. Thanks.